In this video, we're going to talk about continuous compound interest, which is just as it sounds it should be. Continuous compound interest is when the interest is compounded continuously. The formula for continuous compound interest is stated here at the top of the screen. It is A equals capital P base E to the power R times T, where A is the future amount, P is the amount initially invested or borrowed, R is the annual rate as a decimal, and T equals the time in years. Notice I did not define the letter E, and that is because E is not a variable. E is actually a number that is the same all the time, no matter what. Some of you may be familiar with the number pi, where pi equals 3.14 and continues on forever. E is a similar number. The decimal approximation for E is 2.71828 and so on. So E is a number that remains the same no matter what. It has a value of approximately 2.71828 and so on. So technically, when you're working with the continuous compound interest formula, you can substitute E as being this decimal approximation, 2.71828. It's best, though, to use your calculator to compute with E. You'll get the most accurate answer that way. And so things to keep in mind as you're using the continuous compound interest formula, if you'll notice, point number 4 here is I suggest that you use your calculator to compute with exponents and the number E. And if you're not sure how, you can consult the user manual for your calculator or ask your instructor. If you'll let your instructor know the calculator brand and model, they can tell you the keystrokes that you need to use in order to calculate with exponents and with E. So going back to the other things that we need to keep in mind, the rate, when we are given that rate as a percent, we need to go ahead and change it to a decimal. When we substitute a value for T, we just need to keep in mind that T is a time in years. When we work with the continuous compound interest formula, it's important to follow the order of operations. Number 5, we will not round until our final answer. This is to make sure that we end up with the most accurate answer possible. And number 6 says to solve for R or T, which, if you'll notice, the variables R and T are in the exponent of this formula. If you're ever asked to solve for one of those, we're going to use a strategy whereby we take the natural log of both sides. So if you're not familiar with what the natural log is, I'm going to show you how that works in the second example that we do. And so you'll have a better idea of how we do that. So let's go ahead and do our first example. In our first example, we're asked to use the continuous compound interest formula to find the amount A, given that P is $9,000, R is 7.64%, and T is 7 years. So we are told to use the continuous compound interest formula, so we can go ahead and write that down on our paper, E to the RT. And now we can go about substituting the values that were given to find the value that is missing. So we are being asked to find the value of A, so I'm going to leave A as A. The value for P is $9,000. E stays E in the formula. And in the exponent, R is 7.64%. We need to change that into a decimal, so we'll move the decimal point 2 places over to the left-hand side, and that gives us a decimal value of 0.0764. So when we substitute R into the formula, we're going to use 0.0764. and then we multiply that times 7 years, or just 7. Now that we have all of the values plugged into our formula, we can go about solving for a. Since a is by itself here on the left-hand side, finding the value of a is just a matter of simplifying this right-hand side. So following the order of operations, we would do anything in parentheses first. And although we don't see any parentheses in this case, we can kind of think as of this exponent as being in parentheses. We need to go ahead and multiply 0.0764 times 7 so that we know the power to raise e2. So if you use your calculator to find that value, 0.0764 times 7, you should get 0.5348. And I'm going to rewrite everything else here. When we apply the order of operations to a continuous compound interest problem like this, I recommend that you do things just one step at a time so that you don't make any kind of goofy mistake. So I'm going to rewrite everything else, and then instead of writing 0.0764 times 7, I'm going to write what that is equal to, which again was 0.5348. Now, according to the order of operations, we need to calculate the exponent. So we're going to go ahead and calculate e to the power 0.5348. Using your calculator, when you do that multiplication, or I'm sorry, that exponent, you should get, well, I'm going to rewrite everything else here. A equals 9,000, and instead of e to the 0.5348, when you put that into your calculator, you should get 1.707106787. And I wrote out that entire long decimal because we want to reserve rounding until the very end of the process so that we have the most accurate answer possible. Finally, we're going to multiply 9,000 times that decimal. When we do that in our calculator, we should get $15,363.96. Since this is a dollar amount that we're looking for, I'm going to round to the nearest cent. And so the amount using the continuous compound interest formula is $15,363.96. Okay, let's tackle our second example here. Again, we're told to use the compound interest formula. In this case, we're going to find t, given that a equals 82,000, p equals 63,163, and r equals 8.7%. We can go ahead and change this 8.7% into a decimal by moving the decimal point 2 places to the left. I'm going to add a place holding 0, and so 8.7% is equal to 0.087. Sometimes it's good to change r when given as a percent to a decimal, just simply so that you have already done that and it's something that you don't forget. So now that we've done that, we can write the continuous compound interest formula on our paper and substitute the values that we know. So in this case, we know that A is 82,000, P is 63,163, E is left as E, R is 0.087, and T is what we're trying to find, so we're going to leave that as T. Notice that T is in the exponent. That's the situation where we're going to need to involve the natural log of, we're going to involve the step of natural logging both sides. But before we do that, there's one thing that we can do beforehand. In order to isolate t on the right hand side, we can go ahead and divide by 63,163. So we can get that number out of the way. when you put 82,000 divided by 63,163 into your calculator, you should get 1.298228,393. And on the right hand side, we still have e to the 0.087t power. Okay, in order to isolate this t, we need to get it out of the exponent. The way that we do that is using what we call the natural log. Instead of writing out the words natural log, we abbreviate this as lowercase l, lowercase n. So when we take the natural log, it looks like this. We're going to natural log the left-hand side, 1.298228,393, and we're going to natural log the right-hand side. And so we're going to natural log e to the power 0.087t. Okay. Your calculator should have a natural log button. It should have the letters LN on there. In most cases, you can simply hit that natural log button and then the number inside the parentheses. Your calculator, though, may be a little bit different, so if you're not sure how to calculate the natural log, please contact your instructor or look it up in the user manual for the calculator. But when I put the natural log of 1.298228,393 into my calculator, the answer is 0.2610005604. That takes care of the left-hand side. I'm going to give myself a little bit more room here. As for the right-hand side, when we natural log the expression e to the power of 0.087t, what this allows us to do is it allows us to move this exponent down in front as a multiplier. So in other words, I can rewrite this as 0.087t down in front times the natural log of e. So natural logging both sides, the only reason that we do that is so that we can move the exponent down in front of the natural log as a multiplier so that it's not locked into that exponent anymore. And this is where the magic happens. Okay, the natural log of e is equal to 1. So in other words, when we multiply 0.087t times 1, it leaves us with just 0.087t on the right hand side. I'm going to rewrite the left hand side also just to keep everything on the same line. So since the natural log of e essentially disappears, it equals 1, and we know that 1 times anything equals just that thing. We can let that fall off. We can let that be absorbed into the right hand side here. And so our last step in this process is simply to divide both sides by 0.087. Oops. And we're going to divide the left-hand side by 0.087 so that we are left with t on the right-hand side since the 0.087 cancels out. And to determine what t equals, we're going to throw this into our calculator. So 0.26100005604 all divided by 0.087 should give you 3.000006442. And if we round that to the nearest whole number, that gives us t equals 3. And recall that t stands for a time in years, so we would label this as t equals 3 years. So going back to the original problem, if this were a continuous compound interest situation and you had an initial amount invested or borrowed of $63,163 at an interest rate of 8.7%, then in approximately 3 years, because we found T to be 3, that money would grow to $82,000.